cominciano sempre come alle 8 cominciano alle 8 quarto mattina.
Ah, il quarto d'ora accademico però.
Sì.
Però scusa, se cominciate alle 2:15, cioè, e poi finite alle 4 meno un quarto, praticamente fate un'ora e mezza di lezione.
Un'ora assolutamente fantastica.
Mi adeguo, se volete, non è un problema. Io non ho problemi.
Ho sempre fatto molto su chi lo fa più, se ti fa prima pausa, se ti comincia prima dopo.
La pausa non la sto facendo in quelle di 2 ore perché non mi ricordo chi mi aveva detto meglio non fare la pausa e usciamo prima. Sì. Perfetto, io contentissimo.
Sì.
E fare pausa, uscire prima e cominciare dopo comincia a diventare un pochettino complicato, ragazzi. Voglio dire, siete voi che pagate questo servizio, siete voi che pagate me in questo momento. A me è tutto a posto, quanto meno parlo, la voce ringrazia. Però, sai, non è che si può tagliare di qua, tagliare di qua, tagliare mezzo. Io ripeto, se volete fare poi una pausa, si fa una pausa pure cioè, quando facciamo le 3 ore, d'accordissimo a fare la pausa perché io non ce la faccio a parlare per 3 ore, ma manco 2 ore e mezza, voglio dire, anche senza fare 3 ore. Quando facciamo le 2 ore, così avevo capito che preferivate finire prima. Va bene. A cominciare fra 4-5 minuti pure mi sta bene, anche perché poi alla fine vedo che in questo momento ci sono 5 buone ore, no? Sono 5 persone online, 5 più 3, 8. Al corso si sono iscritte 53 persone. 8 su 53, questo batte tutti i miei record personali. Cioè, ho fatto un corso di teoria dei gruppi che effettivamente alla fine c'aveva 4 persone che mi seguivano su una trentina di iscritti. Forse quello era un po' peggio a livello di numeri.
53 non è nessun corso, 53 iscritti. Per i miei sono 10 anche gli altri corsi.
Ti giuro che sono 53 o 54, più di 50 iscritti. Più di 50 iscritti sicuro. Guarda, credo che questi numeri possiate vedere pure voi, non so se vi collegate poi. E questo è tra l'altro sono rimasti stupidi un po' tutti perché gli anni passati, da quanto ho capito, il numero di iscrizioni si attestava sulla trentina di persone, 26, 27, 28 persone. E quest'anno c'è stato un boom grosso, quindi si è arrivati a più di 50 persone, 53-54 persone. Poi immagino che quelli che siano iscritti adesso al corso siano tutti quelli che siano iscritti al primo anno del master. Non lo so voi come lo chiamate, se laurea magistrale o master all'inglese, quello che volete. E poi, le persone che seguono, oddio, ieri eravamo una quindicina, probabilmente arriveremo una dozzina pure oggi, voglio dire, in questo momento siamo 6 e 3, 9, arriveremo una dozzina, 12, 13, 14. Voglio dire, sono stato studente anche io, ho fatto le stesse cose pure io. Non credere che io non ho fatto la stessa cosa di seguire un mese e poi dire sì, vabbè, ciao, ci vediamo all'esame, chi si è visto si è visto. Vabbè, alright guys, time is it. 2 and 10, alright, yeah, probably we can start if this is working. Is it working? Yes, it's working. So, what did we do yesterday? Yesterday we talked about the Wpb approximation. So we introduced Wpb approximation, which is basically this kind of technique that you can use to find an approximate solution to ODE, to ordinary differential equations that are that can be written with the highest derivative term multiplied by a small constant. So basically, very large expression for saying that the Wpb approximation is a technique that you can use to find approximate solutions to ODEs where you have something like epsilon times state variable prime prime plus something else. So we have solved in a couple of situations these WKB, we have used in a couple of situations these WKB approximations. We have said that the WKB approximation is some kind of standard technique in quantum mechanics. Actually, it's very funny because today in my research I was exactly doing these kind of things. So, and we have also given an example of the way you can use WKB approximation for finding large eigenvalues of a initial value problem or boundary values problem. So, but basically, to find large eigenvalues of a differential problem. Before finishing yesterday, even if a bit in a rush, well, but in any case, in a rush or not, this is a kind of introduction that was easy to discuss in a few minutes. We were also trying to discuss the idea of asymptotic expansion. So we have seen that sometimes you have some problems like the one which is stated here. Here. You have some differential problem on which you can find easily enough a solution. So this is a solution of this differential problem, which is an easy solution, inverted comma easy. The point is that you cannot find a closed form to express this solution, this integral. Well, in principle, you can find it, but I mean, if you don't know the specific special functions which are describing this kind of integrals, well, you are basically obliged to live with this expression. The point is that sometimes you don't even need a closed form to express your solution. We were saying yesterday. Sometimes what you need is just the behavior, the asymptotic behavior of your solution. So how your solution behaves. For example, in this case, we were studying the case, we were looking for the behavior for very large lambda. At the end of the day, who cares of the fact that the solution is some sine, some cosine, some exponential, if you're able to say my solution behaves like 1 over lambda when lambda is very, very large. If you need just to know this, well, it's enough to know this. You don't need to write then the solution explicitly. So the idea was to try to develop some methods which allows you to arrive to this kind of information, to arrive to formulate this kind of observations and to be able to find these observations, this information, sorry. And the typical case that we were looking for is the case of this integral, which is exactly of the same nature of the integral that I showed you before, so the same nature of the integral of the exponential minus lambda t squared. Well, this is more general. This is an integral which is it's a functional of lambda. Actually, it's something which is going to give you some expression of lambda, and you want to understand what's the behavior of this integral when lambda is very large. You have some hypotheses. For example, the hypothesis that g is an increasing function in the interval AB, which is exactly the case, for example, of this, because in this case your G would be S squared, and S squared is strictly increasing in the interval 0, t. And we were studying a way for finding the behavior of this integral for large lambda. What did we do? We basically split the interval into two parts. The first part, which is some integral between 0 and t, and the other integral between t and infinity. T is a fixed, well-defined quantity. And what we said is that the second part of this integral, I mean, this is true even if you have other kinds of functions rather than sine t over t. So the second part of the integral, the interesting thing is that you should be able to constrain this function. Indeed, what we were saying is that this function is constrained to be 1, and this way I can say that this integral is basically constrained to be less or of the same order of this stuff here, which for very large lambda goes to 0. So basically this is again very long. To make a long story short, it was just to check that the second contribution of the integral is for large lambda is irrelevant. So basically the relevant contribution for large lambda to your integral is in the first part, which is this thing here. And we have studied, and we have seen how to perform this integral. Actually, this integral is easy enough to be calculated also with paper and pen. The idea is that I can choose t to be capital T, to be small enough to take the Taylor expansion, so to take the, as an approximation of the function sine t over t, to take the Taylor expansion of sine t over t as an approximation of this function. And if I do this, I'm able to perform the integral, model the fact that you must calculate these kind of integrals, which are the important typical integrals that you find in these problems. Why I'm repeating all this story? I'm repeating this story because what I want to do is to generalize this kind of situations when you don't have integers numbers. So basically what I want to do is to introduce some generalization of the factorial, which is given by a special function that's called the gamma function. In such a way we can have a generalization of the theorem that allows me to express the behavior of this integral at large lambda. So a generalization of the factorial is given by this kind of function, which is the gamma function, which is defined as the integral between 0 and infinity of some u to the power x minus 1 times the exponential of minus u in the u, where x is defined to be larger than 0. Just a second, because I think that I did some calculation on this, but I don't remember where did I do the calculation. Should be this one, right? If you prefer to open the window, we can also open the window. All right, all right. No, va benissimo. So, why this thing is supposed to be a generalization of a factorial? Because basically what you can prove is that gamma of x plus 1 is equal to x. This is not definition, this is equal. Is equal to x times the gamma of x, which is basically the same idea of a factorial, right? Because if you have n factorial, for example, n factorial, what is n factorial? Is n times n minus 1 factorial, correct? So basically, this is a kind of generalization when you have a continuous variable as x rather than an integer like n. This is more or less the idea. And you can prove this. I mean, you can prove this this expression. Indeed, you can write the gamma of x plus 1. What's the gamma of x plus 1? This is the integral between 0 and infinity of u to the power x plus 1 minus 1. Correct? Times the exponential minus u in the u. So basically this is the integral between 0 and infinity of u to the power x times the exponential of minus u in the u. How can we evaluate this? We can evaluate this thing. You can do this integral. This integral is not very easy to do. Actually, you have to integrate by part. So the first part, if you integrate by part the exponential, you get minus u to the power x e to the power minus u, evaluated between 0 and infinity. Remember that your variable of integration is u, okay? And then you have plus the integral between 0 and infinity of the derivative of this power u to the power x, which basically gives x u to the x minus 1 times e minus u in the u. Now, what's the first term? So in the first term, I mean all these things. In the first term, you have to consider first of all the limit for u that goes to infinity. But the limit of this thing for u that goes to infinity goes to 0 because I have an exponential of minus u. Then I have the limit for u that goes to 0. For u that goes to 0, the exponential goes to 1. But then I have 0 to some power x, which goes to 0. So basically, the first term goes to 0. Okay. What do I have in the second term? In the second term, I have an x that I can factorize. I can put here outside x. Integral between 0 and infinity. Oh no. All right, then we have the integral between 0 and infinity of u to the power x minus 1 times e to the power minus u in the u. And this is again x, and this thing here is well, that's the definition of gamma of x. This thing. So this gives me x times gamma of x. Basically tells you that gamma x plus 1 is equal to x gamma x. There are some special values for the gamma. Actually, if you specialize to integers, you obtain the standard factorials. Gamma of n, where n is an integer, is n minus 1 factorial. Don't get stressed by the minus 1, okay? It's, also gamma of 1/2. I'm just writing this because that's a kind of value that you always find in problems. Gamma 1/2, it's equal to the square root of pi. Okay, all this introduction to the gamma function is just in order to introduce a theorem, which is called the Watson lemma, which is a generalization of the theorem of the lemma that allows you to approximate the integral, this integral here, when lambda is large, in something that looks like this. So the Watson lemma states the following. I'm gonna copy what's written here in the in my notes, which is copied on the book actually. Given an integral I, a function I of lambda equal to the integral between 0 and b of t alpha h of t e to the minus lambda t in the t, where you have the following conditions. Alpha is larger than minus 1. H of t has a Taylor expansion around 0. Not only this, h of 0 is different from 0. Not just this, but also the modulus, the absolute value of h of t is less than k times the exponential of ct on the interval 0b. The interval 0b is this integral, is the interval on top of which you are integrating. Okay? Here, k and c are two positive constants. So if all these things happen, then what I can do is to approximate the integral with what? With the sum for n that goes from 0 to infinity of this expression, the nth derivative of h evaluated in 0 over n factorial times lambda alpha plus n plus 1 times the gamma function evaluated in alpha plus n plus 1. This is the asymptotic expansion of this kind of integrals. So this expression holds when lambda is very large. So you would say, yeah, okay, nice expression, what shall I do with this? Well, anytime that you get an integral like this one, and believe me, it happens many times that, that in problems, different problems in applied mathematics, you get this kind of integrals. In this situation, you can approximate the integral when lambda is very large with this series, with this expression. Since I was not able to sleep tonight, and since I'm extremely good and nice as a lecturer, I will not oblige you to study the proof of this theorem. But just to tell you that basically the idea of the proof of the theorem is very similar to the idea that we employ here. Okay, this is indeed some kind of simplified version of Watson's lemma, if you want. Instead, we can see we can do kind of a simple exercise to see how is it possible to use this lemma to evaluate, for example, this integral. The integral, what's here?
Sorry, but the gamma we wrote here is the same as we...
That's the gamma function. That's the gamma function we have defined before. Why that's the gamma function? Basically because n is an integer, 1 is an integer, but alpha you don't know anything about alpha. Alpha can be any real number larger than -1. So the only thing that you have to fulfill is alpha larger than -1. Well, you can have situations in which your problem tells you that alpha is an integer, can be 0. If alpha is 0 or another integer, then what you would have is that gamma becomes a gamma of alpha plus n plus 1, which is now an integer. And since it's an integer, you can write gamma of an integer like integer -1 factorial. That's actually the case of the example that I would like to give you, but in any case, I'm leaving this as an expression in gamma. So if you try, for example, to evaluate this expression, the integral between 0 and infinity of the exponential minus t squared times the exponential of minus 2 lambda t in the t. Why this expression? Actually, this is some kind of random expression, but that's not so random. Actually, this expression is somehow related to the error function of lambda, where the error function is in turn something which is related to this integral here. Just to say that this is not just an expression for doing a random exercise. So if you want to evaluate this thing, how do you do it? First of all, you have to reduce your integral to something that looks like this integral here, if you want to use the Watson lemma. So what shall I do? First thing, here there is an exponential of minus 2 lambda t. Here I have an exponential of minus lambda t. So I shall reduce to e to the minus lambda t. So what I can do is to define some tau, which is equal to 2t, in such a way that I have, well, the tau is equal to 2 dt, so the 1/2 of the tau is equal to the t. Okay. Well, and also t is equal to tau divided by 2. If I do this, I can rewrite the integral as, okay, exponential of minus t squared becomes the exponential of minus tau squared divided by 4. No magic here. the exponential of minus 2 lambda t becomes the exponential of minus lambda tau. Fair enough. And then that t becomes that tau divided by 2. Now I have an expression that is very similar to this one that is here on top. Why? Because I have the exponential of minus lambda times a variable, which is here. Then I have t to the power alpha. What is t to the power alpha? Right. T to the power alpha is basically 1. So basically means that I'm considering alpha equal to 0. This is the case in which I can apply the Watson lemma for alpha equal to 0. Let me write somewhere. All right, so to apply the Watson lemma, I need an expression like this one. So I have the integral between 0 and something. In this case, the something is infinity. So this is an integral between 0 and infinity. Then I have the exponential of minus lambda t. Exponential minus lambda t. A function, we will discuss in a second the function, ht, which is going to be this other one. Okay? And then I need something like t to the power alpha. I need to find this power alpha in order for understanding what's the alpha that I need here. In this case, alpha is equal to 0. If alpha is equal to 0, I have t to the power 0, which is 1, which is basically this thing here. Okay? So basically I can apply Watson's lemma for lambda large, alpha equal to 0. Okay. So what do I get? I get, no, sorry. There is another thing that we have to check, and that's the function h. So the function h needs to be different from 0 in 0. But in tau equal to 0, this is 1, because this is exponential of 0, which is 1. Okay. So, check. We must have a Taylor expansion around 0. That's an exponential. So, you have the usual Taylor expansion of the exponential around 0. So, it's not a problem. Check. And the last thing, you have to check that the absolute value is constrained by some exponential which is linear in C. This is the only thing that probably you should check by hand. If you check it, in any case, you're able to prove that this is also true. What you can do, for example, is to expand, to Taylor expand this thing. I don't remember what's the expansion of the exponential of minus tau squared. In my laptop. Well, in any case, you can easily expand both the exponential of minus tau squared over 4 and the exponential of some positive number times tau. You will discover the exponential of minus tau squared over 4 is always less than the other one. So also this other condition, what is this one, is fulfilled. Check. So the exponential of minus tau squared over 4 is a good candidate for the function h of for having the role of ht in my Watson lemma. Now that I checked also all these things, I can say that what's a lemma applies, and I can just calculate the large lambda expansion. So what shall I do? This is going to be this sum here. So in particular, if I want to calculate there is a 1/2 here in front, which is coming from this, and then I have I directly wrote. So what you have to do is to calculate the single derivatives of these things and evaluate these derivatives in zero. So what's the zero derivative? The zero derivative is the function itself evaluated in zero, which is giving you 1. So the first term is going to be 1 divided by I'm considering the n equal to 0, so this is 0 factorial times lambda to the power alpha is 0 plus n, it's the first term, so n is 0 plus 1 times gamma of 0 plus 0 plus 1. Now, what's 0 factorial? Right. So this is 1 divided by 1 times lambda. So this is lambda times gamma of 1. This is the first step. The second term is going to be the derivative of this, which is minus 1/4 times 2 tau exponential of minus tau squared divided by 4, evaluated for tau equal to 0, which is
0.
Which is 0. So the second term, useless the time, well, I can just complete for completeness, but this is going to be 0. Then you have to do the second derivative, so you have to derive, you have to calculate the derivative of this quantity here and to evaluate in tau equal to 0, so the second derivative of the exponential. Guys, it's a derivative. Don't ask me to write now all the derivatives. I can tell you directly what's the result, which is going to be minus 1/2. The second derivative of this exponential here, evaluating tau equal to 0, is minus 1/2, which is multiplying gamma of 3 divided by 2 factorial lambda cube, well, etc. You continue this way. So basically this gives you 1/2 times 1 over lambda minus gamma 3 over 4 lambda cube plus higher order terms. So this is an approximation, the asymptotic expansion for large lambda of the integral of this integral here. Okay. Actually, as I told you, I'm a bit cheating, not cheat, but gamma 3 I could have written 2, because gamma 3 is 2 factorial, which is 2. So basically, for this problem, the gammas that appear in these problems are gammas of integers, and gamma of integers have this nice expression here. However, if you have alpha, which is not 0 and not an integer, then you will have some non-trivial expression for the gamma function. That's all about this. Any question before changing completely topic? Popolo da casa? People at home? Any question?
No, sir.
Very good. Then we can change. We can start to study something which is completely different, which is somehow more related to usual topics in applied mathematics, which is, in this case, orthogonal expansion, Fourier series. The equivalent of Fourier series. Did you see Fourier series during the first 3 years? No.
Ho visto solo io.
And at home, people there? You know the idea of Fourier series. So we are going to study some kind of generalization of Fourier series. Well, we are also including Fourier series. But you remember the Taylor expansion. So if I consider suppose that I have a function f of x, which is which is continuous with infinite continuous derivatives. You know what does C infinity means, no? It's a function which is continuous, which has infinite derivatives which are continuous themselves. So suppose that this f is C infinity in some point x naught. Then you remember that you can express f of x as a Taylor expansion. So I can write f of x as sum for n that goes from 0 to infinity of some coefficient a n times x minus x naught power n divided by n factorial, where the coefficients a n are defined as the nth derivative of f with respect to x power n evaluated in x naught. So this is Taylor expansion. Now the Fourier series are very basically they are just an alternative to Taylor expansion. It's an alternative to Taylor expansion if you have some integral function in so f in f tilde integrable in minus pi, then I can write f tilde of x as a naught divided by 2 plus the sum for n that goes from 1 to infinity of a n sine n x plus bn sine n x, where a n are coefficients which are defined as 1 over pi integral between minus pi and pi of f tilde x cosine n x, and bn So 1 over pi integral between minus pi and pi of f tilde of x sine nx dx. So this is the Fourier series. What's useful in Taylor expansion and what is useful in Fourier series? So why you should use the Taylor expansion? Why you should use the Fourier series? So basically, you use the Taylor expansion whenever you are looking for a good approximation very close to the point x naught, where the function is of plus c infinity, right? So you want just a very, very good approximation locally in one point. If you want just that approximation in that point, well, use the Taylor expansion. That's going to be the best approximation that you can use in your problem. On the other hand, if you want instead an approximation that works globally, or that works, for example, in this case, in the interval minus pi, in particular, by chance, your approximation is an approximation of some signal, which is a periodic signal, for example, then you use the Fourier series, right? So usually signals that you can study, electric signals, whatever it is, you have some kind of periodicity. If they have some periodicity, the best thing that you can do to approximate this signal is to study the Fourier series of the signal. If you have a problem, you want to understand, you want to approximate the function very close to one point because you are interested to understand what happened exactly close to that point, then use the Taylor expansion instead of the Fourier series. What we want to do, what we want to start to do today is to generalize the idea of Fourier series. Basically, when you are expanding Fourier series, what you are doing is expanding on some basis, which is you are using some set of functions which are sine and cosine. You are not very obliged to use just sine and cosine. That's actually the idea that we want to generalize. We want to generalize the idea of Fourier series in such a way that I can use also other functions to approximate, to expand my functions as a matter of the best set that I can choose and use for the approximation. Now, the next half an hour is going to be a bit boring because there are a lot of definitions. So the idea is that well, we want to introduce a set of function f, which are said to be square integrable in an interval AB. So we say that f belongs to the class L2 on AB. Do you know what does this mean? Do you remember what does you remember? No, you don't remember. So basically, this means that the integral between a and b of the modulus squared of f is finite. Again, you can say this saying that f is of the class L2 on AB. So f is square integrable, the modulus squared is integrable, on the interval AB. Now, what we can do is to define some inner product between functions of this space. So the idea is that this L2 has some structure as the structure of a space. You remember, for vector space, you can define an inner product with some properties you can define a norm. That's actually the same thing that we are gonna do for the case of L2 well, for the case of these functions f. So the first thing we define an inner product, scalar product, what do you call it? Which I write in this way. If you have vectors, you know how to do this, right? If I have vector a scalar product with the vector b, this is gonna be something which is like something like this, right? Very good. So what I want to do is to define a inner product, a definition, an inner product for this. My inner product in this case is gonna be the integral between a and b of f of x times g of x in the x. This must be the
Is this scalar product?
actually this is called inner product because it's more general. Inner product. If you refer to vectors, many times you find scalar products as well. So this must be defined for any f and g that are in this L2AP. Now, is this a good scalar product, inner product? In order for being a good inner product, what you have to do is to verify that some of the typical properties of inner products are fulfilled. In particular, it must be symmetric. That's actually as for scalar product of vectors. But this is easy because basically these are functions that they commute. So you can write the integral of on AB of fx times gx, which is equal to the integral on AB of gx times fx. So this is trivial. Then you must have a linearity. So f of g plus h is equal. Sorry, the inner product of f with g plus h is equal to the inner product of f with g plus the inner product of f with h. But again, this is trivial because this is equivalent to the following linearity of the integrals, right? And then I want the inner product of f times alpha g equal to alpha times the inner product of f with g, where alpha is some real number. Alpha, yeah, in this case is a real number. This actually must be true for any alpha real. And this must be true for any f, g, and h belonging to L2 on AB. But this is for any alpha real and for any f and g belonging to L2. Again, this is a trivial property because this is basically a property of integrals. That if you have the integral of alpha f times g, this is equal to alpha times the integral of f times g. Nothing different. What else? You can define a norm. You can define a norm. What's the idea of norm when you have, so this can be defined as the square root of the inner product of f with itself. What's the idea that you have of norm of a vector? What's the norm of a vector? Usually, for the usual definition. So let's try to understand. Let's try to comment again with all these properties in our connection with the world of vectors. Okay, we say that this inner product is the equivalent for function of the scalar product that we have for vectors. This is a definition. For vectors, you can define the usual scalar product as we have seen before. The only thing is that the scalar product is an inner product itself, so it has to satisfy all these properties, which actually are also satisfied by this inner product of functions. Now, when you have vectors, what's the scalar product of a vector for itself? So this is gonna be something like the sum of AI squared. AI are the components of the vector, no? So what is this quantity? Imagine that you are in 3 dimensions. In 3 dimensions, you have a vector A, which has 3 components: AX, AY, AZ. And then I'm calculating this thing here. This thing here is giving me AX squared plus AY squared plus AZ squared. What is this thing? This is scalar, but physically, what does it represent? The modulo squared. Okay, what is the modulo? That's the length of the vector. That's exactly the norm. So this thing here is the norm squared of this vector for this scalar product. So basically, I can write, instead of writing this thing this way, I can write this in this notation, right? And if I take the square root of this is the length of the vector. The length of the vector would be the norm of vector, right? But this is for the vectors, okay? This is 3D vectors. We are now reasoning on functions. Basically, you can do the same thing also with functions. So we have defined an operation, which is the inner product, which has the same properties of the scalar product, which allows me to define a norm as for the usual scalar product for vectors. And full stop. This is actually the equivalent. This would be the equivalent of a length of vectors, but for functions. This thing would be then equal to the square root of the integral between a and b of modulo fx squared. Here I'm just using the definition of the inner product of my inner product. Okay, do you remember the idea of orthogonality of vectors in geometry? When it happens that 2 vectors are orthogonal. That's San Gennaro, guys. So when it happens that 2 vectors are orthogonal in geometry, 2 3D vectors. Right?
And their product is
Which product?
The scalar.
So when the scalar product of the two vectors is 0, so if I have an A and B, which are two 3D vectors, then if this thing is 0, I can say that A is orthogonal to B. That's good. Then I will use exactly the same kind of definition for functions. So if I have two functions, f and g, such that the inner product of f with g is equal to 0, then I say that f and g are orthogonals. Remember that basically this means that this is the integral between a and b of f of x times gx in the x. If this happens, then I say that f and g are two orthogonal functions. Then if I have a set of functions f1, f2, f3, blah, 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 this is a set of square integral functions. So all these sets are of class L2 on ABE. So this set is said to be orthogonal if for any fi and fj that I choose, the inner product is equal to 0. This is for any I and j. Basically, I'm just choosing two functions between this set. Example. Let's see a couple of examples. Of two functions which are orthogonal and two functions which are not orthogonal. So let me consider cosine of x and sine of x on the interval minus pi, pi. Cosine of x and sine of x on the interval minus pi and pi are basically two of the functions that appears in the Fourier series. It's not by chance that I'm choosing this one. So I want to see if on the interval minus pi, pi, the two functions cosine of x and sine of x, if they are orthogonal or not. So what I should do is to calculate this integral. And now you know the question. What is this integral? How much is this integral? Lo sai? No. Fai questo integrale. C'è una maniera abbastanza più semplice per farlo. There is a very easy way to do this. What's the integral of sine? Cosine. No, cosine. So if I have sine squared of x, what's the derivative of sine squared of x? 2 sine of x cosine of x. So this thing is 1/2 sine x squared evaluated between minus pi and pi. What is this? So basically this tells you that on the interval minus pi, pi, the two functions cosine x and sine x are orthogonal. Now, will you, I'll leave you as an exercise to check what happens for other combination of sine and cosine. So basically, this thing here. Try to do this integral. Okay. What instead I want to check is what happens for example, let's try what happens for power for powers of x. So let's see if what are the functions that I have here. If x and x cubed are orthogonal on some interval a and b. Questions: are x and x cube square integrable functions in AB? Is this true?
Not for x cube.
Not for x cube. Why? Remember that square integral means that the integral of the square of the function, of the modulus square of the function, is finite. So this basically would mean that the integral between a and b of x cube squared, so x to the power 6, is finite. Is this finite? It's a strange number, but it's finite. So basically this means that both x and x cube are square integrable functions on an interval AB. So we can ask ourselves if they are orthogonal on the integral AB. So basically this means that I should evaluate this integral. But if I evaluate this integral, this is the integral between a and b of x to the power 4, which is x to the power 5 divided by 5, evaluated between b and a. This is again a strange number, but this number is not 0. But even if a is equal to 0, this would not be 0. I mean, the only possibility that you have if you want to play on b and a is that b and a are both 0. Or if b and a are the same. But if b and a are both the same, this basically means that you are doing an integral. So that would be 0 by definition, right? The point is that that's actually another good exercise that I'm now thinking about. Thank you very much. That's actually thanks to you that we have this exercise. The idea is that try to find two polynomials which are orthogonal on, let's say, an interval 0, 1. So try to find p of x and q of x such that this is true.
Looking to a plot of two functions.
Looking to a
graphic
A plot, okay.
Of function. I can use if they are orthogonal. So, for example, two
No.
lines perpendicular lines.
No, forget about, no, okay, no, right. Forget about now the idea of perpendicularity, of orthogonality that you have from geometry, okay? Forget about that. Your definition of orthogonality is this one. But that's actually the same definition that you have in geometry. The fact that then you have this shape, that's another thing. But the idea also in geometry is that in order to be orthogonal, you must have the inner product, in that case scalar product, equal to 0. For two functions to be orthogonal, you must have this inner product, so this kind of integrals, equal to 0. Full stop. That's your definition. Ok? Dov'è che io dicevo questa cosa? Parecchio più no? So I will comment a bit on this kind of exercise later, because actually there is also a trick for finding orthogonal functions, orthogonal vectors in general, which is to use a procedure that you surely remember from geometry, which is called the Gram-Schmidt orthogonalization procedure. This is an algorithm. I mean, it's a formula that you can apply and you can find in this way orthogonal vectors, starting from a set of functions. So the idea is that you can start, for example, in this case, from a set of functions which are square integrable on the interval 0, 1. And this set of functions can be 1, x squared, x cubed, blah, blah, blah. We have seen that if I take just two of them, well, it doesn't work. It's like this case here. Indeed, what I have to do is to find suitable combinations of these functions. And these Gram-Schmidt orthogonalization procedures give you the chance exactly of doing this thing starting from this function. In any case, we will comment on this later today. Before having a break, because we will have a break. Yeah, the only thing that I just would like to add is the following. Do you remember what is the definition of, what is the meaning of having a normalized vectors? Normal vector. Yeah, exactly. So basically, you can translate this idea also in the case of functions. So as you can imagine, we have defined a norm, which is the equivalent of the modulus of the length of the vector. So we have defined the norm of a function, which is this object here. So suppose that I have a function which is square integrable. And that the norm of this function is this. Then what I can do is to define a new function, a new vector in M2, if you want, which is this one. right? And this guy here is a function with norm equal to 1. Because if I'm taking the norm of this object, this is going to be equal to 1 over the norm of f times the norm of f, which is equal to 1.
Il versore.
È l'equivalente del versore nel caso delle funzioni. In particular, if you have a set of functions like these ones that we wrote before, you remember we say that this one is an orthogonal set of square integrable functions, right? Because fi, fj were reciprocally orthogonal. If in particular this fi and fj has norm equal to 1, this is an orthonormal set. Okay, if apart from this, you also have that the norm of fi is equal to 1, then the set is not just orthogonal, but is orthonormal. E sono le 3:20 and I think that we can stop for 10 minutes. Calmo ragazzi, calmo.
Scusi, prof, può andare un po' più giù con la slide, per favore?
Anche senza per favore, non ti preoccupare, ti ringrazio, non l'avrei fatto comunque. Ecco, dici.
Grazie.
Ah, solo questo, vabbè.
I'm sorry, Professor, I have a question. Can I ask?
Yes, yes, absolutely yes. Tell me.
The example that you wrote, the second part that you wrote, the tau is equal to 0. I can understand how did you calculate it?
I don't understand which example you are speaking about.
About London. No, it's
probably here.
yes.
Probably here.
Yes. Here.
This one or the one?
Yes, the second part.
The second part, this one.
Yes, here. Yes.
Okay, but this one, what I've done, this quantity here is the derivative with respect to tau of the exponential of minus tau squared divided by 4, evaluated in tau equal to 0. So what is this object? This object is the derivative of the exponent, which is minus 1/4 times the derivative of tau squared, which is 2 tau.
Yes.
Times the exponential of minus tau squared divided by 4.
Yes.
But
But I can't understand that. Why do you wrote d divided by d tau? I saw it, but the formula that you wrote.
All right. So basically, I'm applying what we have called the Watson lemma. I'm applying this formula here.
Yes.
Okay, in this formula here, I have this expression. The first term, this factor here, you see, this is this h, this is the nth derivative of h evaluated in 0.
Okay.
H in my case is the exponential, is this exponential of minus tau squared divided by 4.
Yes.
I'm applying this formula on this integral, right?
Yes. Yes.
This object here is my h. So what I do is to calculate the derivative of this object and evaluate the derivative in 0. This n tells me the derivative. So n equal to 0 is going to be the function in 0. N equal to 1 is going to be the derivative of the function in 0. N equal to 2 is going to give me the second derivative of the function in 0, and so forth and so on. Okay?
Yes.
So what I've done here is, in the first term, I have the function is the derivative 0 of the function. So it's the function itself evaluated in 0. If I evaluate this function in 0, what I have is 1, because it's the exponential of 0, which is 1. That's actually this one. Then the second term is the derivative of the function in 0. The derivative of the function is this object. If you evaluate this object in 0, what you get?
Yes, Professor. Thank you.
That's it.
Yes.
Okay?
Yes. Yes.
And then you have the second derivative in 0, which should give you this minus 1/2, etc. Okay?
Yes. Thank you.
Okay. Okay, guys, we can start. So what we want to explore now is the following possibility. Suppose that I have a function f which is square integrable on some interval ab. Can I expand this function in a series of given orthogonal set of functions of which are square integrable in a B? So can I write f of x equal to the sum between n that goes from 1 to, sorry, the sum of n that goes from 1 to infinity of a n f n x, where the fn are also square integrable on a b? And no. That's actually the kind of question that we would like to answer now. Let me start by defining an approximation of the function f of x that I obtain by truncating this series. So let me define
Fn are orthogonal functions.
Fn are orthogonal functions. Yeah, it's a set of orthogonal functions square integrable in AB. Let me write it. Okay. So let me define this quantity that I obtain by truncating the series. So let me define this as the sum between 1 and capital N of a n f n of x. This basically define me a quantity which I can call capital E with n of x, which is given by f of x minus s with n of x. This is basically f of x minus sum between 1 and n of a n f n of x. How much is this? What is this?
The sum from n to
Actually, this is a very bastard question, because no, that's not that sum. The idea was that you were answering that is that sum. But the point is that we want to prove if it's possible or not to write this thing in this way. Until this moment, we don't know anything. So that's actually the kind of expression that we can write. But bravo, that was the idea. The idea is to provoke this answer. No, we cannot say, at the moment, we cannot say anything. What we want to do is to see if it's possible or not to write the function f, to approximate the function f, with this series with sum of from n that goes from 1 to infinity of this an times fn. But for the moment, let me write this quantity capital E as f of x minus the sum. This is what is called the pointwise error. Why it's called the pointwise error? Because basically it tells you in a given point x, what's the difference between the real function f of x and this truncated series sum between 1 and n of an fn. If I choose a point x which belongs to the interval AB, if I have the limit for n that goes to infinity of the pointwise error, if this thing here goes to 0, then I say that f of x, well, the other way around, sorry. As we then converges pointwise to f in IB, in the interval AB. Of course, if I'm doing all these things, it means that I can have some kind of alternative definition of errors. What I can do is to define indeed some kind of integrated error, which is what's called the mean square error, which is defined this way. You can define the small e with n, which is defined as the integral between a and b of the modulus squared of f of x minus s with n of x. And if I'm using the expression of s with n, this is the integral between a and b of the modulus squared of f of x minus sum between 1 and n of an f n x squared dx. So what is this object? Do you recognize this object? This small e. Now, the small e, look at this quantity which is here. So basically what's called the mean square error gives you this is actually the norm of the pointwise error. Well, the norm squared of the pointwise error. What can happen is that instead of having this condition here, so instead of having the condition that the limit for n that goes to infinity of the pointwise error goes to 0, what I can have is that the limit for n that goes to infinity of the mean square error goes to 0. If this happens, we say that S with n converges to f in the mean square terms. In the mean square sense. Note that you can have situations in which one is true and the other is not true. So that's actually why you need the two different conditions and two different definitions of errors and two different definitions of convergence. What I would like to I would like to concentrate on one of the two concepts, ideas of convergence, and in particular, what I would like to concentrate is the second one, the convergence in the mean square sense. So suppose that S converges to a function f in the mean square terms, in the mean square sense. This basically means that if this happens, I can write f as the sum from 1 to infinity of a n f n of x, which is the expression that I wrote here upstairs. Right? Is this expression here? So if I can do this, if I can write this thing here, this means that I can also calculate eventually the inner product of the single of the function f with the single functions f m. What is this inner product? This is the inner product of the sum between 1 and infinity of a n f n of x times f n of x.
Fm is one of the Fn functions.
Fm is one of the orthogonal functions. Now I'm using linearities, the linearity of the inner product. So I can write this as the sum between 1 and infinity of a n times the inner product between fn and fn. So what's this quantity? And this is not a bastard question. You can calculate this. So let's try to think loudly. We know that the fm's are orthogonal functions. No? What does this mean that they are orthogonal functions? That the inner product is 0 if I take two different functions. If I have the same function, the inner product gives me the norm square. So basically this means that this quantity here can be written as some delta and m, delta, which is equal to 1 when n is equal to n. Quella delta. So delta n m, which is equal to 1 when n is equal to m, times the the square of the norm, square of the norm of Fm. Right? This is nothing else than the inner product of Fm with itself. If I put this here inside, what I get at the end is An times delta Nm. I'm summing over all the n. This is Am. See? So mi soddisfa? Is this okay?
No.
No, okay. So if I'm summing between 1 and infinity on n, and I have this expression here. I'm summing on all the n. So suppose that I'm taking, for example, m equal to 3. If I'm summing on all the n, this means that I will consider A1 delta 1 3, delta 1 3 is 0. A2 delta 2 3, delta 2 3 is 0. A3 delta 3 3, delta D3 is 1. So basically this means that all the terms of this sum are all zeros apart for the term for which n is equal to 3. Or in general, apart for the term when n is equal to m. That's actually why here I get a m times the norm of the square of the norm of Fn. This coefficient am that I can write in this way, am. So I'm taking this expression now. This equal to this. I can write am as the inner product of f with fm divided by the norm of fm squared. These coefficients here are what? Are called Fourier coefficients. What happens if this set is not just orthogonal but is orthonormal? The norm is equal to 1. So this thing is going to be equal to 1, and the am is the inner product of FFM. It's going to be just the numerator. So basically this gives me a prescription which is the following. If I can say that so whenever I'm in the situation where I can ensure convergence in the mean square sense in an interval AB, so convergence for functions in L2IB in the mean square sense, then what I can do is to express the function f, the integral square function, the square integral function f, as this series here, where the coefficients a n can be calculated in this way, where the coefficients a n are the Fourier coefficients with respect to this set of functions. Note that we do not we didn't say anything about the particular set that we are considering. the particular set of function f of m. We didn't say anything. Basically, what you can do, we will see in a moment. You can specialize to the case in which these fm are sine and cosine, and what you get is exactly the Fourier series. But before doing this, what we would like to do is the following. First of all, close the door because it's a bit. What we want to do now is to ask the following question. So suppose that instead of using the Fourier coefficients, I'm using some other coefficients. So I have defined these Fourier coefficients an, and now what I want to do is to compare the approximation that I have of my function with the sum of these functions fm, which are weighted with some other coefficients. So, in summary, what I want to do is to compare the approximation that I obtained of the function f with the series, heterogeneous series, the Gibbs function, in terms of Fourier coefficients. These an are these Fourier coefficients. And I want to compare this with the approximation that I can obtain with some other coefficients, whatever they are. I don't specify these coefficients. What is the purpose of this? What I would like to prove is that the combination that I obtain through the Fourier coefficients is the one that is minimizing the mean square error. So this kind of combination is the combination which is minimizing this quantity here. That basically means that this thing should hold.
Minimize the pointwise error, right?
Minimize the mean square error. This is the norm squared of this thing. This is a norm. Remember, this is basically the integral. What's written here is the integral on between a and b of this function squared, which is the mean square error. And let's do the calculation because it's useful. It's long, but it's useful, unfortunately. So let's calculate explicitly this norm here, b n f n norm squared. So we've said that this thing here is the inner product of what is written here with itself. Means that is this quantity. Oh dear. Sum between 1 and n, b n f n with itself. Sum 1 n, b n f n. Okay? So now what I can do is to use linearity of the inner product and to split this inner product in different parts. So what I have is the inner product of f with itself Then I have minus this times this, so it's minus the sum of Vn times Fnf. Then I have this times this, which gives minus sum between 1 and n of f Bn Fn. And then I have this times this, which gives plus the double sum Bn Fn Fn. Quanto è scandaloso? Specialmente l'ultimo termine, especially the last term. Do you understand the last term?
One sum is gram, the other sum is gram.
Yeah, basically I'm just changing, this is a sum, the sum is mute, so basically I can change, I can call this m, that's the same. Not the same. I'm just calling the index in another way. This sum is mute, this index is mute. I can change, I can call it Pepe if you want. This would be the sum of Pepe of B Pepe F Pepe. So this is the sum between on n and m of Bn Vm Fn Fn. Inner product Fn Fn. What happens here, guys? Ma lucidano, ma veramente si fa? Okay. So what do we have here? What do we have here? You remember that actually there is the property of inner products, which is symmetric, if I'm changing Fn with F. So basically this term here and this term here are the same, are equal. So I can write this as, well, the first term is the same, norm squared of F. Then I have minus 2 sum of on n that goes from 1 to n of Bn F Fn. And then I have the last term, which is plus the sum of what? How can I rewrite this thing? So this is Bn, then what? What's the Fn, Fm? We are supposing that the Fn are orthonormal, is an orthonormal set. So since this is an orthonormal set, this means that the inner product of Fn with Fm is 0 if n is different from m, and 1 if n is equal to m. What does it mean? What's now this sum?
It's not also the square of the.
No, we are supposing these are orthonormal. We are, I mean, we can do the exercise also for the orthogonal set, but I'm doing the exercise for orthonormal set. So Fn and Fm are orthonormal. So what happens to this term here? How can I rewrite this term here? Here there is a double sum, a sum on n, and a sum on m of bn delta n m.
Split to Samsung.
No, you don't split the sum.
Bn square.
B what?
Bn square.
Bm squared what?
Because if m different to n, it's 0.
So you say that the total is bm squared. All this thing is bm squared?
The sum of bn square.
I like it. This is gonna be the sum between 1 and capital N of bm squared. Is this clear to everybody? Guys at home? Too much silence there. Is it clear?
I'm sorry, Professor, but I can't understand.
Okay, very good. So, did you understand this expression here? This Bn, Bm, delta, and m?
Yes, Professor, yes.
Okay. So now what I have to calculate is the sum over n of the sum over m of Bn, Bm delta n m. Now, suppose that I'm doing the sum over n. Okay? When I'm doing the sum over n, remember that delta n m is equal to 1 for n equal to m and 0 for n different from m. Okay? But if I'm doing the sum over n, I'm surely arriving to the number m, whatever it is the number m. Suppose that the number m is 1000. Then I have to sum over n. I will sum from 1 to 1 million. And I will surely touch 1000. So this basically means that I will surely find the number n for which this is n is equal to m. When n is equal to m, these things will be bm times bm times delta mm, which is 1. This thing is 1. So this would give me bm squared times 1. Sum over m. Because the sum over m, I didn't do the sum over m.
Okay, Professor, thank you.
Okay. Let's cancel this. Okay, now what I'm doing is this. adding and subtracting this quantity. I put plus 17 minus 17. Okay, let me write in this other way that probably is better. Okay. Okay, I'm adding and subtracting the same quantity. What are these object here? The inner product of f with fn. We have defined these things before. Bravo. So basically this means that here I can put together this object here, this object here, and this object here. And what I get with these three objects, again, this index is mute. I can call it M. That's the same, doesn't change anything. So if I'm putting together these two things, these three things, what I get is the sum on M that goes from 1 to capital N of Bm minus Am squared. What do I have still? I still have this, the inner product of f with itself, and then I have these terms here, minus sum from 1 to n of Am squared. Now, what can I do now? Well, I can do the following. I want to put together this and this object. In order to put together these two things, what I want to show is that these things are equal to the square root of the norm of this object here. I want to prove that these two objects, 1 and 2, are equal to this.
Each of them, or
Both together. So I will do it, I will start from here and I will find these two terms because probably it's more clear. But the procedure is the same that we have followed for the Bn. So basically this is the inner product of f minus the sum with itself but this is equal to the inner product of f with itself using a linearity, using linearity. Inner product of f with itself minus sum of an times the inner product of fn with f minus sum am the inner product of no. E questo è frustrante proprio. Minus sum am f f m minus plus double sum then and then of an fn fn. This is the same expression that we did before, that we wrote before for b, but now it's for a. What's the difference? Okay, this thing is the same. Here I have twice sum of an times an, which is these two together, and then I have plus sum of am delta n. That's the same thing that we have done before. Which is the inner product of f with itself minus 2 sum of an squared plus sum of an squared. Va bene? This cancel with one of these. So what you get is the inner product of f with itself minus the sum of an squared. That's actually the result that I was looking for, right? Somebody at home? Qualcuno ha detto qualcosa? No, allucinazioni, mamma mia, 40 anni, brutta cosa. That's actually the result that I was looking for. The square of the norm of this thing here is equal to the norm of f, the square of the norm of f, minus this sum. So I can go back to my calculation, my original calculation. Here I have exactly the square of the norm of f minus this sum. Giusto? No, ma dai. Ma non è possibile, dai. Ma possono fare quello che vogliono le macchine. Okay. So the point is that now I can finally write these two objects here, as we have proved, as this, as we have just calculated here. Okay? Plus, I still have this term here, the sum on m that goes from 1 to capital N of Bn minus am squared. Okay? And we have arrived finally at the result where we wanted to arrive. Why? Because this quantity here, what do we have in this quantity? We have this quantity is always positive because it's the sum of the square of numbers. Right? This is always positive. If this is always positive, means that the sum of these two is surely greater or at most equal to this. It's first term plus second term. If the second term is positive, you know for sure that the sum of the two is surely larger than just the first term. Siamo d'accordo, siamo tutti d'accordo. And that's the end, guys. This is actually the proof of what we were looking for. So we were trying to understand if it is true that the combination that I have that I can write using Fourier coefficients is the one that minimizes the mean square error, which basically means that this condition is true. And this is exactly the result that we have found in this calculation. From here to here. Fantastic. Any problem? Any question? It is clear. So finally, what we can do is probably what you are more interested in or not, is to specialize finally to the case in which you have sine and cosine, in which your orthonormal functions are sine and cosine. So basically, we will specialize to the Fourier series case. So suppose that the function f is now a square integral function on it is an integrable function on minus L. Then I can write the Fourier series of f as the following. A naught divided by 2 plus the sum between 1 and infinity of a n cosine n pi x divided by L plus bn sine n pi x divided by L, where an is equal to 1 over L integral minus L and L f of x cosine n pi x divided by L, and the bn is equal to 1 over L integral between minus L and L f of x sine n pi x divided by L in the x. Usually the kind of expression that you find in Fourier series are those when you specify the interval to be minus pi. So usually you find for L equal to pi, which is a particular case of a generic Fourier series of this. So in this case, what are my function fn? So my function f will be, well, there is also 1, then cosine pi x over L, cosine 2 pi x over L, etc. Sine pi x over L, sine 2 pi x over L, etc. Which are basically all these ones which are here, plus 1 which is here. Now, suppose, for example, that I want to calculate the Fourier series of something easy. Let's consider f of x equal to x in the interval minus L, L. What would you do? You would like to write this expression here, right? In this expression, what are the things that I don't know? What I don't know are the coefficients. The only things that I have to calculate are the coefficients, because these are functions. These are the functions, the orthogonal functions which constitute, on top of which I'm expanding my f. So what I have to do is to calculate the Fourier coefficients. How do I calculate the Fourier coefficients? Using this couple of formula, which are these ones, which are exactly the formula that you obtain as the inner product of f with the single f of f with n. This thing here is nothing else than this, where f with n is either cosine or sine of n pi x divided by l. So if I want to calculate, for example, this thing for my function, for this function here, what do I have? An is equal to 1 over L integral between minus L and L. Yes.
F of x equal to x, I choose it.
That's actually, I'm trying to write the Fourier series of this function. I'm choosing it. So you have a function. When you are basically these things, all these things, it's useful because you want to express wherever is the function in terms of sine and cosine. So I'm doing this for a function which it's easy, but you can do for any function. What you should do is to do integrals, basically calculating these coefficients. So the An is going to be these objects here, and the Bn is going to be this here. What say 0? It's this one. Which is equal to 0. I can give you the result for the other ones. Actually, this is going to be equal to 0. And this is going to be equal to 2L over n pi times minus 1 to the power n plus 1. So once that you have calculated these objects, you can finally write your Fourier series of the function f of x, which is gonna be 2L over pi that multiplies sine pi x over L minus 1/2 sine 2 pi x over L plus 1/3 sine 3 pi x over L plus higher order terms. So basically what I've done is just to rewrite this expression here with the A0, AN, and BN that I have calculated. So with these objects here. If you do that, you find this. Now note that we are considering the fact that this function converges in the mean squared sense. Okay? In order just to show you very, very briefly that the problem with pointwise and mean squared convergence, you can do the following. You can
Excuse me, Professor. I
Yes.
have a question. In the line before the last line, we have 1 divided by L, x square, okay? And we have L and minus L. This minus, I don't think it could be 0. I'm not sure about that 0 because it will become positive.
I can calculate here. This is 1 over L times x squared divided by 2 evaluated in L minus x squared divided by 2 evaluated in minus L. Correct?
Minus L will be, oh, right. I get it. Thank you.
Okay.
Sorry.
No, it's okay. Don't worry. Fine. All right. So I was saying, problem about pointwise versus mean square convergence. If I'm using this series, this Fourier series, what would be the value of f in L? I mean, if I'm using this, you should calculate the sign of the sign. Bravo. This would be 0. What would be f of minus L? So calculate the sign here. This would be 0. What is the value, the real value in L and minus L? So this is what happens if I'm using the Fourier series. But if I'm instead calculating directly the limit on the function that I have, which is x, this would give me f of L equal to L, f of minus L equal to minus L. What does this mean? This means that the function does not converge pointwise, because it does not converge in the point L or in the point minus L to the corresponding Fourier expansion. the thing which is written here in this part. And this should give you an idea for appreciate the fact that these two convergences are indeed different objects, and one does not imply the other. Actually, there is also another interesting aspect, which is the following. If you take the derivative of f of x of this thing, the derivative of this is 1. If you take the derivative on the right hand side of this beast, of this object, you don't get 1. No. Okay, so you should also pay attention and be careful when you are considering this thing.
So this one is not a good approximation.
No, this is a good approximation, but it's an approximation in the sense, in the mean square sense. So you can say that f converges to the Fourier series, which is written on this right hand side, in the mean square sense. It does not converge to this thing pointwise, because it does not converge in L or minus L.
So when you use this to calculate the behavior of the function, what value in a specific one?
That's correct. Also, actually, here there are other aspects that probably what time is it? All right, very quickly. This is the last thing before finishing, and I do not want even to do this completely. I would like to leave it up to you. In any case, there are the calculations on my notes. These are trivial calculations, are algebra calculations. So let me consider the following example. Suppose that I would like to calculate the Fourier series for a function f of x, which is defined in this way. Okay, this is equal to, this is a step function. So basically it's a function which is minus 1/2 between minus pi and 0. So, like this. And then it's equal to 1/2 between 0 and pi. And what I want to do, what I would like to do is to write the Fourier series for this object. So in order for doing this, I have to do again the same calculation. So what I have to do is to calculate the Fourier coefficients, these numbers a n. In this case, the interval is between minus pi and pi, so this is going to be 1 over pi integral of minus pi and pi of fx cosine n pi x divided by pi. I can simplify these two things here. What you should do here is to split the integral into two parts. So you should split this integral between minus pi and 0 plus the integral between 0 and pi. Right? Because in the first integral you put f of x equal to minus 1/2, and in the second integral you put f of x equal to 1/2 times cosine nx blah blah blah. If you do this integral, do the exercise, what you find is this is equal to 0. Then you have to calculate the Bn, which are 1 over pi integral minus pi and pi f of x sine n pi x divided by pi. Again, pi you can simplify. And you do this integral in the same way. 1 over pi, you split the integral minus pi 0 and integral 0 pi. In one of the two you use minus 1/2, in the other one you use 1/2. What you find is this expression, 1 over pi times 1 over n minus cosine n pi divided by n. I'm writing directly the results of these integrals, but these are really trivial integrals. And again, the calculation, all the calculations are on this piece of paper. In such a way, if you write the Fourier series of f of x, that I remember, let me remind you that this is minus 1/2 for x between minus pi and 0, and 1/2 for x between 0 and pi. So the Fourier series is going to be equal to the sum between 1 and infinity of 1 minus 1 to the power n divided by pi n times the sine of nx. You can try to do one thing. You can try to plot this sum for a limited number of terms. For example, you can consider the sum of the first 3 terms, the sum of the first 7 terms, and you can plot it. So the first term is giving you something like this. So the first term, in the sense, just the first, if you're considering just n equal to 1, which is the sign. So basically, it's giving you a sign. The sum of the first 2 terms is giving you something like this. You can go on, and you can see what happens for the sum of the first 3 terms, the 4 terms, and blah blah blah. So this is a kind of phenomenon that happens when you have discontinuities. So f of x is a function that is not continuous, right? In 0, there is a jump. On the left is minus 1/2, on the right is equal to 1/2. As a result, you can still approximate the function with its Fourier series. What you would obtain is this kind of phenomenon, which is called the Gibbs phenomenon. Which is related to overshooting. So basically, the function that you get, the approximation that you get, the Fourier series, the approximated Fourier series that you get is approximating a bit more or a bit less, and then oscillating around what's the real value of the function. And this is going to be true whatever is the number of terms that you are including in your truncated Fourier series. So you will always have this approximation, this up and down around the real function. It's like sorry, approximating what? Why? Ah, ma non... Allora, assolutamente, le serie di Fourier vengono utilizzate esattamente per queste cose qua. I mean, not necessarily you will have this kind... indeed, a true signal is never a step function. A true signal, you will never have a perfect step function signal. So, basically, your signal is always going to be some continuous signal, which can be more or less approximated even in a better way with this Fourier series. In any case, yes, Fourier series indeed are usually used for approximation of signals, any kind of signals actually, periodic ones. Okay, I think that for today could be enough. Any question before closing?
Sorry, Prof, I missed the last part of this page. Yes, only the what you write. Yeah.
So, what did you miss? This part here.
Yes.
All right. So,
Is the final
scusa, non ho capito. Vuoi che lo rispieghi o semplicemente che non l'hai scritto?
No, se lo può un attimo rispiegare. Cioè, è la soluzione finale o è un...
No, certo. Okay. Yeah, sure. So basically, what I've done here is here there is an equal sign that disappeared. So I calculated the Fourier coefficients for this function here, and I've written here and there. So these are the Fourier coefficients for this function. Then what I did is to write the Fourier series of the function f. The Fourier series is a naught divided by 2, a naught is equal to 0, plus the sum of an cosine of nx plus bn sine of nx. An and bn are written here. So what I've done is just to rewrite this thing. So a naught is equal to 0, an are all of them equal to 0. There is just these terms here, bn times sine nx, which are these. So you have sine nx, and then the bn, which are, well, you can rewrite these as 1 over n pi times 1 minus cosine n pi. But the cosine n pi is equal to minus 1 to the power n. That's exactly this expression that's here. So this is the Fourier series for this function. And then what I've done is this plot. So this plot here is the plot for f, for the real f. And then I plot this curve here, which is basically this sum with just the first term, n equal to 1. And then I plot this other curve here, which is this sum up to n equal to 3, I think, up to n equal to 3.
Okay, thank you.
That's okay. Good, guys. Have a nice week. Talk to you next week on Monday. Thank you very much.
Arrivederci, prof.
Thank you, Professor.
Ciao, buona serata. Cheers.
Goodbye.
Bye bye.
Thank you, Professor.
Salute.
Bye.